Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we're going to discuss another important topic. Our topic is, let me write it, enumeration of modes. I write in the bracket density of states of a continuous medium. So this is our topic. We have to enumerate the modes and we will find the density of states of a continuous medium. So let me underline it. Listen to me carefully to understand the concept. Okay, consider the elastic waves. We have already discussed the elastic waves in a bar. So I have a bar, right? Let me name it figure 1. So it has certain length. L. So consider the elastic waves. So I write, consider the elastic waves in the long bar of figure 1. Remember, we have already discussed the idea of elastic waves, and we are assuming that the wave travels in one dimension only. So I write, consider the elastic waves in the long bar of figure 1 in which the wave travels in one dimension only, right? We have discussed the solution. The solution is, which we discussed in the last lecture. What was the solution? Solution was that of the plane wave, and we wrote it this way: U is equal to A e raised power iota times qx minus omega t. A e raised power iota qx minus omega t. So this was our solution, which we have already discussed. This solution was the solution of the wave equation which we constructed in the last lecture by applying Newton's second law to the waves, to the wave motion of this bar. So I named this equation first. You remember the symbols. A is the amplitude of the wave, Q is wave number, omega is angular frequency, X is position t is time, right? Now for the current discussion, what we do to the solution, we omit the time dependence or temporal factor for the current discussion. We omit the temporal, that means time. We omit the time dependence. We omit the temporal or time factor in the solution of, in the solution, which is our equation 1. We have, when we do that, we have this equation. I will write with another color. U is equal to A e raised power iota qx. This is my second. This is simply equation first written without time dependence. We have omitted I minus I omega t in the exponential. So we are writing just A e raised power iota qx. Right? Because this is not relevant for us. Even if we take it, our results are going to be same. Now, next is we have to consider the effects of the boundary conditions on the solution, equation second. So I write, now we consider the effects of the boundary conditions on the solution two, that is this equation, right? And you must remember the boundary conditions are determined by the external constraints applied to the ends of the bar. For example, the ends of the bar, one end is this and second end is this. The ends of the bar might be clamped. You can fix the ends, clamp them as the interior of the bar vibrates, or they might be free to vibrate with the rest of the bar, right? Now the type of the boundary condition which is convenient for our calculation is known as periodic boundary condition. So we use periodic boundary condition. What is periodic boundary condition? I will use another color. Periodic boundary condition means that the right end of the bar is constrained in such a way that it is always in the same state of oscillation as the left end. I should write it in the bracket. So this periodic boundary condition means the right end of the bar is constrained in such a way that it is always in the same state of oscillation as the left end, right? So this end and this end has same state of oscillation in periodic boundary condition. It is as if the bar were deformed into circular shape so that the right end joined the left. I repeat, it is as if the bar were deformed into circular shape so that the right end joined the left. Now, given that the length of the bar is L, so if we take origin as being at the left end, so if this is the origin, so here x is 0, and then here x is L, right? So one end means x is 0, second end means x is L, because L is the length of the bar. Now how can then we write the periodic condition? So periodic, therefore, the periodic condition, by condition I mean boundary condition, means that, what it means u at x is equal to 0 is same as u at x equal to L. Understand it, don't confuse. I'm saying displacement, u is what? It is displacement of the particles of the bar. So displacement at particles of the bar at both ends is same, because we are using periodic boundary conditions. That means u at x equal to 0 is same as u at x is equal to L. So we are imposing boundary conditions. Boundary condition simply means what is the condition we are imposing externally on the bar at the ends. So now u of x equal to 0 is equal to u of x equal to L. It means u at x equal to L. This is u at x equal to 0. So I name this condition as equation 3. This is my boundary condition, where u is the solution given in equation 2, this one, where we have ignored the time, right? Now if we substitute where's my pen? Let me get my pen back first. If we substitute what happened to this? Where's pen? Let me check it out. This is my pen. If we substitute equation 2 into equation 3, we find that understand it. If we substitute equation 2, that's our solution, into equation 3, that is our boundary condition, we find e raised power iota ql is equal to 1. And I need 4. I encircle it. It is simple. You are writing ux of 0 and equating that to ux of L, where u is given by equation 2. So you are writing ux of 0 means you are putting x is equal to 0. When you do that, e raised power 0 is 1, you will get a. So your left hand side will be a. Then in right hand side, you write ux of L. Your ux of L is, you put for xl, that is a e raised power iota ql, right? So when you do that, I will write it in the rough. You write a equal to a e raised power iota ql. Got it? From left hand side, ux of 0, that is a. When you put 0, it is 1. Then right hand side, it is u at x equal to L. When you put x equal to L, it becomes a e raised power iota ql. So you do that, a will cancel out. So you will get e raised power iota ql is 1. I name it equation 4. E raised power iota ql, e raised power iota ql is 1. Now this equation, let me write it on the next page. This equation imposes a condition on the admissible values. Admissible values means allowed values. Admissible values of Q. Only those values which satisfy this equation 4, are allowed. So you can see putting a boundary condition is putting a condition on admissible values of Q, right? Only those values of Q are allowed which satisfy equation 4, right? Now note that now e raised power iota n to pi is 1 for any integer n. So we conclude from equation 4, that is this equation, restriction on the values of Q, that the allowed values are Q equal N 2 pi by L. Q equal to N 2 pi by L. I name this equation as equation 5, where N can be 0, plus minus 1, plus minus 2, etc. So only these values of Q are allowed according to our boundary condition, right? So when these values, when these values are plotted along a q-axis, they form a one-dimensional mesh of regularly spaced points as shown in figure 2. I will draw figure 2. So we're plotting these allowed values of Q along a line. So let this be O point origin. Then there are values of Q plotted along this line. Spacing between the two points representing Q is 2 pi over L. This is my figure 2. It is showing us allowed values of Q, right? The spacing as shown in the figure between the points is 2 pi by L, right? So when the bar length is large, the spacing becomes small and the points form a quasi-continuous mesh. We need to understand each Q value of equation 5. I should write it in red. Each Q value of equation 5, that is this equation, or you can say each point in figure 2, because each point is representing a value, allowed value of Q, or each point in figure 2 represents a mode of vibration. Understand it. That means, I underline this mode of vibration. That means under the imposed boundary conditions, This bar can vibrate in multiple ways. Each way is a mode, right? And those ways are governed by the boundary condition 4 and allowed values are presented by equation 5, right? I stop here. This is all for today. We will continue this topic in the next lecture. Don't waste your time, go through all the video lectures, prepare your exams, and don't forget to subscribe and like my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.